am Mrs. K. Anbuselvi, Associate Professor of Computer Science, VV Vanniperumal College for Women, Virudhunagar. In this video, we are going to discuss about the Banker's algorithm to avoid the deadlock. This algorithm, which consists of two algorithms, one is safety algorithm, another one is resource request algorithm. The Banker's algorithm is applicable to a resource allocation system with multiple instances of each resource type to avoid the deadlock. When a process requests a set of resources, the system must determine whether the allocation of the resources will lead to the system in a safe state or not. If it will, the resources are allocated to the requested process. Otherwise, the process must wait when some other processes release the resources and it is acquired by the requested process. Now we will discuss about the safety algorithm, which is used by the resource request algorithm of Banker's. This algorithm, which consists of two data structures, work and finish. These two variables are vectors with size m and n respectively, where m represents number of resources in the system, where n represents number of processes in the system. Initially, the vectors work and finish is initialized as work is equal to the available number of resources in the system, whereas finish of I is set as false for every processes I varies from 1 to n. In the second step, we have to select an I such that the finish of I is equal to false, and we have to check the need of the requested I is less than or equal to the available number of resources, that is work. If no such I exists, the control list goes to the step 4 in order to raise an error. Otherwise, we are moving to the third step, where we have to set the finish of I is equal to true. That is, the process I finish its work and it releases the resources. Now, the work becomes work is equal to work plus the allocated resources in the process I. The procedure is repeated till all the processes complete its task and whose finish of I value becomes true. Now, in the fourth step, we have to check if all the processes are finished, means finish of I value becomes true. Otherwise, if any one of the finish of I value is equal to false, means it is not possible to construct the safe sequence, which implies that the system becomes unsafe state. Otherwise, the system is safe. So, the algorithm which returns a Boolean values, that is either true or false. If it returns true, means the system is in safe state. Otherwise, the system becomes unsafe state. The deadlock may occur. Now we will move on to resource request algorithm. When a request for resource is made available by the process Pi, the following action should be taken. First, we have to check whether the request of the process I is less than or equal to the need of the process. If it is, then we can go to step 2. Otherwise, we have to raise an error conditions. In the second step, again we have to check whether the request of the process I is less than or equal to available number of resources in the system. If it is, then we can move on to step 3. In the step 3, we have to change the variables. We have to modify the variables, that is available, allocation and need. The allocation is decreased by subtracting the requested resources from the available number of resources. Next, the allocation vector is increased by adding the requested process to the allocated resources to that particular process I. In the third step, the need variable, that is the need vector for the process I is decreased by subtracting the requested resources from the need of that particular process I. Now, we have to call the safety algorithm, which is discussed in the previous, to check this scenario which change the state as safe state or not. If the system is safe state means then we can actually allocate the requested resources to the process I. Otherwise, we have to restore the data values. That is, the system becomes unsafe, the deadlock may occur. Now we will implement this algorithm by using an example. The problem is the system which consists of 5 processes with 3 instances. The 5 processes are named as P0, P1, P2, P3 and P4. The 3 resources are A, B, C, where A, the resource A which consists of 10 instances, the resource B which has 5 instances and the resource C which has 7 instances. Suppose at time T0, the following scenario has been taken place. That is, the allocated resources is mentioned with the help of the allocated vector and maximum need of each and every process in the system is maintained by the maximum vector, and the available number of resources currently available is mentioned by the available variable or available one-dimensional vector, and the need of all the processes in the systems with the help of need vector, and it is calculated by subtracting the allocated resources from the maximum resources requested by all the processes. Now suppose at this time the process P1 which requires the resources 1, 0, 2, that is 1 instance of resource type A, 0 instance of resource type B and 2 instances of resource type C. Now we are using resource request algorithms in order to modify the variables allocation, available and the need. Initially, the first step is the request is compared against the need. If the request is less than or equal to the need of the process, that is, here the requested resources are 102 and it is compared against the need of the process P1 that is 122. It is valid. Therefore, we are moving to the next step. That is, we are checking whether the requested resources are less than or equal to currently available number of resources in the system. Here in this example, the requested resource is 102 and the currently available number of resources 332 and it is also a valid one. Now, we are moving to change the variables available. That is, the requested resources are subtracted from available number of resources currently in the system, that is 332 is subtracted from the 102 is subtracted from 332 and now the value becomes 230. Next we will change the allocated resources to the process P1. That is, it is increased by adding the requested resources to already allocated resources to the process P1. Here in this example, it is 102 is added with the 200 which is equal to 302. Now next we have to change the need vector, that is the need values which is allocated to the process. It is decreased by subtracting the requested resources from the already values which is stored in the need. That is 102 is subtracted from 122. Now it becomes 020. At this stage, we have to check whether this scenario which lead the system an unsafe state or unsafe state. This can be done with the help of the safety algorithm which is discussed earlier. When we are using the safety algorithm, we have to construct a safe sequence. Initially, according to this safety algorithm, first we have to select the first process in the system, that is P0. We have to check the need of the process P0 is less than or equal to the work, where work is represented as available number of resources in the system. Here in this example, the currently available number of resources is 230. The need of the process P0 is 743. It is invalid because we are having only 230, but it requires the additional resources 743 and it is not possible. Therefore, this P0 is not entered into the safe sequence. Next, we will move on to the next process, P1. Its need is 0 to 0 and it is compared against the available number of resources, that is 230. It is valid. So, if it is valid means we have to change the available number of resources from 230 to 302. That is 302 is added with the already existing 230. Now it becomes 532. That is currently the system which has 5 instances of resource type A, 3 instances of resource type B and 2 instances of resource type C. Now since it is valid and we are updating the work value, now this process P1 is inserted into the safe sequence. Next we will move on to select the next process, that is P2. Its need is 600 which is less than the currently available number of resources, that is 532. But it requests 6 instances, but we are having only 5 instances in the resource A. It is also invalid. Now we will move on to the next process P3. Its need is only 011, but the current available number of resources is 532 and it becomes valid. Now we have to change the work value and it becomes 743. That is 7 instances in A, 4 instances in B, 3 instances in C. Next the sequence, the process P3 is inserted into the safe sequence. Now we will move on to the next process, which is P4. Its need is only 431, but we are having the number of resources 743, which is greater. Therefore, it is also a valid one and we are changing the work value as 745. And the process P4 is inserted into the safe sequence. Next, we have to select the unfinished processes, that is P0 again. And its need is 743. The currently available number of resources is 745. It is also a valid. Now we have to change the work value as 755. Next, we have to select the unfinished process, that is P2. And the need of the process P2 is 600. And it is compared against the currently available number of resources, which is 745. Now it is also a valid and it is changed as 1057. The work is changed as 1057. It is the resources which is initially allocated, which is in A, B, C. So initially we are having A as 10, B as 5 and C resources which have 7 instances. Now we are constructed a safe sequence. The safe sequence is P1, P3, P4, P0, P2, which implies that the system is currently in safe. Therefore, we can originally allocated the resources which is requested by the process P1. Thank you.